So this video is just finishing up the work we had done in section 9.8 where we started to introduce power series. So this is not 9.8 part 2, this is the first notes packet that you got on section 9.8, and we got a chance to talk about radius of convergence, right? Where is a series centered? That's kind of easy to see, right? We figured out now, okay, how to identify the radius of convergence, right? And roughly sort of get an interval. But we have not at this point been specific enough. So if you recall, in example 2, we were working with the series, right, from n equals 0 to infinity, 3 times the quantity x minus 2 to the n, right? So this was a series that it was centered at 2, right? And we found through the ratio test, right, that basically our radius of convergence is 1. So from there, we can kind of conclude, oh, okay, centered at 2, and I can reach out 1 in either direction. Okay, that basically gets us, from 1 to 3. But we've got to do this last little nitpicky bit of, okay, well, should the 1 and the 3 be included or not? All right, and I hate to tell you, sometimes you can't always tell just by looking at it. Sometimes both of your endpoints will be included in your interval of convergence. Sometimes they both won't. Sometimes one will and not the other. All right, so the natural way to do this is to test those values of x, right? So right now, the x values in question are x equal to 1 and x equal to 3, right? So let's see what happens when x equals 1 and x equals 3, all right? So in the case where x is equal to 1, we generate the series, right? 3 times, 1 minus 2 to the n, so negative 1 to the n. And you know what? If you can just tell, right, that a series is going to diverge, I mean, certainly do it, right? You just list out the terms, right? And you're going to get, 3 minus 3 plus 3 minus 3. That's going nowhere in particular. But also, this is a geometric series. It's an alternating geometric series, right? So it's a geometric series. And in this case, your common ratio is equal to 1. So by geometric series, we know that this particular series, right, for this instance of x equal to 1, this will diverge. All right, so I would say that this specific series diverges by geometric series. So currently, our interval of convergence, if I were going to write this using interval notation instead of inequality notation, so our interval of convergence thus far is going to be 1 not included, 3, and then we need to figure out, okay, is the 3 included? All right, so let's do our due diligence here. All right, so let's test and see what this series does for the case of x equal to 3. All right, so we've got 3 times the quantity. Okay, now 3 minus 2 to the n, so that's 1 to the n, and if we could figure out the last one, we can certainly figure out this one, right? This is simply a geometric series with, again, r equal to 1. So this also diverges by geometric series. So our interval of convergence is solidly 1 to 3, but not including either of those. All right, once we hit 1 and 3, our approximation is not going to be so good. All right, so there's your interval of convergence. Now, it will not always be so obvious. We kind of look at this, and because the series that we were given is so obviously geometric, it's kind of easy to see where this is going. But unfortunately, that will not always be the case. All right, so let's go to example 5, all right, and, start looking at some less obvious examples. All right, in order to find the interval of convergence, we first need to find the radius of convergence, right? And so again, we are going to do that with the ratio test. All right, we're going to force the issue. All right, so we are going to say, all right, I want my common ratio to be less than 1 for this thing to converge, so let's force the common ratio to be less than 1. But first, we need to get the common ratio with the ratio test. So here is my n plus 1th term divided by my nth term. And then we're pretty much just going to go and simplify. Right, again, I kind of like to restructure this a little bit, you know, get my x's together, get my n terms together, right? And now it's clear, hopefully, all right, that for this piece right here, this limit as n goes to infinity is going to go to 1, right? And, well, this is not dependent on n, so it is what it is, right? And in fact, right, the limit as n goes to infinity, right, effectively now we're looking at x to the n plus 1 over x, which we can very easily simplify. So that's the limit as n goes to infinity of x. Okay? So in this case, all right, sorry, I should put that back, right? That's our common ratio, x, right? And in order for this to pass the root test, the ratio test, we need that common ratio to be less than 1. So that's what we want. We want the absolute value of x to be less than 1 to be guaranteed convergence. Okay, so, you know, back to algebra. That means that x could be less than 1, or x could be greater than -1. So right now, in terms of an interval of convergence, hopefully you can identify that we are centered at 0 here, right? So we're centered at 0 with a radius of convergence of 1. So let's make a note of that. Your center is 0. Your radius of convergence is 1. So now let's get our interval of convergence. Currently, all right, we are looking at, you know, basically from -1 to +1, and we really just need to figure out, well, do we include those endpoints? All right, so we're going to test each of them. All right, so let me test x equal to -1 in my series. And then, of course, I will test x equal to +1. All right, so if I let x equal 1 in my series, right, I am going to get from n equals 1 to infinity 1 to the n over n, which is really just, right, oh, I'm sorry, this should be a -1 to the n, because I am plugging in -1, not +1. All right, so actually now that really doesn't simplify to much of anything, does it, now that it's negative? So let's just get rid of that. All right, so that's kind of enough for us, right? So when x is equal to -1, we get -1 to the n over n. And now, what does this do? Well, I'm actually going to come back to that. All right, I mean, there are a number of things we can do here. This is not difficult. All right, but let's do the other one first. You'll see why. All right, so if x is equal to +1, now we have the case, I think I was getting a little bit ahead of myself, where we have 1 to the n over n. So really, we're just looking at 1 over n. This, hopefully, you recognize, right, that it diverges by the harmonic series, and that's sufficient. All right, you could just say diverges by harmonic series. The way to formally prove that would be with the integral test. But the harmonic series is common enough that we can say diverges by harmonic series. So currently, for our interval of convergence, the 1 is not included. The -1 remains to be determined. And now I want to come back to this, all right? And hopefully you can see that this is the alternating harmonic series, and we know that actually the alternating harmonic series converges, all right? So let's write that in. This is the alternating harmonic series, but if that were a thing that you didn't know, all right, I would probably use the alternating series test here, right? I would show right, that the limit of the nth term as n goes to infinity, and again, we don't care about the alternating part, right? We want to show that that equals 0, check. And 2, we want to show that this thing is strictly decreasing, the terms, right? Just the numeric terms, the magnitude of the terms. So in other words, we want to show that the next term is strictly less than or equal to the previous. And if you go through the algebra there, that's going to be a big old check mark. So this would converge by the alternating harmonic series test. All right, or I'm sorry, the alternating series test. So this would be a case where, hey, x equals -1, -1 gets to come to the convergence party. It's going to be a joke. I'm making it a thing. All right, the convergence party. So these are the important things here. Centered at 0, radius of convergence was 1, interval of convergence was -1 to 1, right? But -1 was included and +1 was not. All right. That was just way too easy. Let's get on to some trickier stuff. All right, so find the interval of convergence for something that is similar, right? Similar to example 5, but a little bit different, right? It's not x to the n over n, it's x to the n over n squared. Okay, so let's see how that changes things. All right, so in order to find the interval of convergence, we first need to find its center and the radius of convergence. I know up until this point, the radius of convergence has always been 1. That will not always be the case. In fact, hopefully that will change in the next example. Can't remember, but let's give it a whirl. All right, so basically we find the common ratio by doing the ratio test, right? And then force it to be less than 1, or at least see for what values of x will this be less than 1. Okay, so ratio test, go. That's an n. All right, so let's sort of group all my things together here. X to the n plus 1 over x to the n times n squared over n plus 1 squared. Okay, and so now if I simplify, right, I'm looking at my n terms, and guess what? It's degree 2 over degree 2, right? So I can really just compare their leading coefficients. So guess what? As n goes to infinity, that's going to 1. I know. Hopefully one day I'll give you something that's actually tricky. So again, looks like we are looking at absolute value of x, right? So again, all right, it is now the case that we want the absolute value of x to be less than 1. So again, we're centered at 0. The radius of convergence is 1. So, well, here, let's write that all out, right? We're centered at 0. The radius of convergence is 1, right? And so now it's just a matter of establishing the interval of convergence, right? And so that's going to be, -1, +1, but we've just got to figure out brackets or parentheses. So let's test each of those. All right, so let's test x equal to -1, and that is going to generate -1 to the n over n squared. This I would say converges absolutely. By absolutely, I mean absolute convergence, because the all positive version converges, right? If I compare this, against what I get if I make it not alternate, right? That's a p series, right? With p greater than 1. So this can, so the red series converges by p series. So if the red series converges, the alternating version in blue most certainly does. All right. So I'm going to be a little bit less formal here, and I'm just going to say this converges. It's, an alternating p series. With p equal to 2, which is greater than 1. So -1 gets to come to the convergence party. All right, now x equal to +1. Let's check it. Okay, oh boy, what is gonna happen here when x equals +1? Ooh, spoiler alert. I should start doing the positives first, right? Because it's easier to check the positives first and then use that to help you check the alternating versions. Strategy. Okay, so this converges by p-series. Done. All right, so everybody's coming to the convergence party. All right, so here's sort of everything that we need to know about this power series that we've been given, where it's centered, what its radius of convergence is, and what its interval of convergence is. All right, let's see what happens with this last example. I hope that I'm finally giving you something challenging. We'll find out. All right, it certainly looks a little bit more impressive. All right, so to find the interval of convergence, let's first get the radius of convergence by finding the common ratio using the ratio test. All right, so when I take the absolute value, all the negatives from the alternating stuff is going to go away. So I will just use the positive pieces, n plus 1 over 2 to the n plus 1, divided by the nth term. Okay, and so let's clean this up, simplify what we can simplify. All right, let's bring our x terms together. And our two terms together. Okay, and I'm actually going to simplify this a little bit more before I really start thinking. All right, so this is going to leave me with really like an x plus 1 on top and a 2 on the bottom. All right, so n is no longer in the equation. It's this. This is the limit, right? As n goes to infinity, I don't really care what n is doing. This does not depend on n, right? So the limit is, x plus 1 over 2. All right, so that's your common ratio. And you want that to be less than 1. So here is a case where our radius of convergence is not 1. All right, so look alive. All right, because right now, let me show you where we are. Currently, where are we centered? All right, it's always x minus c to the n in a power series. So hopefully, you can conclude that we are centered at -1. Our radius of convergence remains to be determined, and then, obviously from there, all right, we will change our interval of convergence. All right, but let's take a look at why the radius of convergence is not actually 1 here. And it all goes back to algebra, right? If I have the absolute value of a fraction, I can do that, or I can take the fraction of the absolute value, right? In other words, the absolute value of x plus 1 over the absolute value of 2. Oh, but we know what the absolute value of 2 is. It's 2. So then, when we multiply both sides by 2, right, we get this, right? And so this is kind of the state that you want to be in to determine what your radius of convergence is. You really just kind of want to see, the absolute value of x minus c is less than some number, okay? You don't want the absolute value of x minus c over this or times that, right? You really just want that x minus c isolated by itself. So here is our radius of convergence, like for real, okay? So our radius of convergence is 2. So currently for our interval of convergence, right, if we are, right, here's a number line, centered at -1 and reaching out 2 in each direction, right, that puts us at +1 and -3. All right, so we're currently looking to test -3 and 1 as our endpoints. So let's plug them into our series and give it a go. Okay, so first let's test, let's just do n equals, that should be an x equals -3. Okay. And it seems like, a lot, but it's actually not going to be that bad. I know it's like negatives for days, but, multiple negatives, we can usually do something about that. So, all right, if x is -3, this gives us -2 to the n over 2 to the n. Okay, so coming on down here, giving myself a little bit more room. All right, let's tidy this up a bit because right now this is not great to work with. All right, so, the trick to this is to pull out the -1 to the n and separate it from the -2, right? So really, to rewrite the -2 instead as a -1 to the n times 2 to the n, right? That totally works. That's a property of exponents, okay? You know what else is a property of exponents? That -1 to the n times -1 to the n is -1 times -1 to the n, right? Exponents totally distribute into, parentheses over multiplication that way, right? So look how nice and tidy this is cleaning up. So guess what? Now that's a +1 to the n. And, well, the 2 to the n over the 2 to the n cancels. So I'm just left with this. What is this series? I mean, you could say that it's a geometric series with a equal to 1 and r equal to 1. Or you could just realize this is just 1 plus 1 plus 1 plus 1, which is definitely going to diverge. So whatever your justification, right? Diverges by geometric series. All right, so let's come on back. Sorry, -3, you do not get to come to the convergence party. Okay, but now, all right, let's test, let's test x equal to, what was it, +1? Great. All right, so when x is equal to +1, we get from n equals 0 to infinity, -1 to the n. All right, x is a +1, so that is 2 to the n. Yes, over 2 to the n. Well, isn't that convenient? Okay, so let's simplify this. This time the alternating piece does not go away, but these sure do. So we're left with this, which is just an alternating series, which, I mean, this is 1 minus 1 plus 1 minus 1. I mean, obviously it diverges, although there are some ways that people like to argue this converges. We can talk about that later. But right, this would fail the alternating series test, right? Because if you go to check, right, the limit as n goes to infinity of the stuff inside that's not alternating, in other words, 1, that is not 0. So that fails. All right, so I would just say that this diverges by alternating series. Okay, so that's kind of it. So basically at the end of the day, it's like test your endpoints in the series. See what kind of series you get, a convergent series or a divergent series. Be prepared to justify. Good work.